Thank you. Well, this will be quite a contrast because now we are going to learn what happens if you learn entirely too much about arcane language details. So first, maybe what is this talk? Maybe the title seems a bit weird to you. So originally I proposed 2 talks to choose from, basically. So types in D talk and the tuples in D talk. The issue was, like, the types talk fits the conference schedule, but the tuples talk was what everybody wanted to hear. So I'm going to do both, which is what usually happens in D. So basically what I'll do is I will freely associate about this type system for hopefully around 45 minutes. I did cut some of the more arcane type system things in favor of tuples. So first a disclaimer. So we will look at some quite dark corners of the language. So this is not a particularly representative sample of language rules. So here be dragons. So be prepared. So first, let's discuss what actually is a type. So a type is metadata describing the runtime effect of an expression, so in a relatively general explanation. Often, types also classify values for arguments and results of expressions, which is basically the way that D is using the term internally. So like the type of 2 times 3 is int, which means that if you evaluate the expression 2 times 3, you get the result, and the result is an integer. Often, types also track side effects, and indeed we have like all those nice attributes, like pure, safe, and no throw. There's also no GC. Sometimes types prescribe a memory layout, which is the case in D. It's not always the case. So sometimes types just tell you what to expect. They don't tell you how to represent it, and the runtime system can actually choose this for you. So indeed, this is not the case, which means you get control, but the compiler gets less flexibility. You have to do the optimizations yourself. Type information is often partially or fully erased at runtime. So there are languages where you have an untyped language, then you build a type system on top of it. If you type checks, that means things are fine, but you actually don't need to keep the types around at runtime. In D, as some information about the types is kept around at runtime, but not all of it. All right, so one interesting tidbit is that early type systems were mostly about proving consistency or termination. So for example, if you know about the set theory in lambda calculus, there are those tricky things, like this is a set that cannot decide whether it's a member of itself. And this is a lambda term that runs without termination, which is kind of, well, it reduces in one step to itself, right? So you take this function, you substitute it for x here, and then you just get the same term again, which is quite annoying if you want to do logic, because, well, if you want to do logic, you don't like self-referential things. Interestingly, in like modern programming languages, this is very seldomly done. So you don't prove termination, you actually directly introduce language constructs that don't terminate, and they very much type check. All right, so let's jump right in. In D, we have some basic types. You have like short, which is a 16-bit integer, int, float, double, all the jazz. On the right-hand side, you have some expressions that evaluate to a type of that, to a value of the type. So basically, there are values already. And then we store them in variables of the type. So one thing that's interesting here is that this one here, it's actually of type int. We can store it in I anyway, even though in general we cannot store ints in I. So what D does for integral expressions is it tracks the entire range of the type, of the expression, sorry, which works using interval arithmetic, and a nice exercise is actually to derive the best possible interval transformer for bitwise operations, which is one of the things I did, which is now in the compiler. All right, that's I guess as much as we'll talk about value range propagation at the moment. It's quite nice because you get to actually cast things, but you just have to be explicit about cutting off the trailing bits, for example. Then D also has some type constructors. So they combine basic types and also user-defined types in some interesting ways. We can create an array of int. We can say the elements should not be mutated through this reference. We can say the elements are immutable. And then the type system kind of has some checks and guarantees related to that. There's also static arrays that have a fixed size and are value types, whereas here this is actually a reference, which you can see because we update A and we see a change in B. This cannot happen with immutable things because they cannot change for any reference. And finally, there's also associative arrays. So one thing about type constructors is they are magic, and users cannot define their own type constructors that behave in this way, which is maybe a less desirable property. All right, then another thing that's D actually copied from C and C++ is there are Lvalues and Rvalues. I mean, it's quite standard in modern programming languages, which means expressions behave differently when they're on the left-hand side or on the right-hand side of an expression, and some expression can only appear on the right-hand side. Some types are actually only meaningful for Lvalues, but you can still get Rvalues of the type. So for example, here we have an enum n. So this is an R-value of type const int, and the value is 5. So it's a bit confusing what the constant actually is, because it's actually just an int, right? And you also cannot assign a new value to 5, even though it's of type int and not of type constant. This is because you cannot assign to R-values. Fun fact, in early versions of Fortran, I think you could actually do this, and then everywhere else in the program where you used 5, it would then actually just be 6. This is not the case in D. D is a sane language, of course. Then so Lvalues you can usually update, except if they're const. But well, here m is not const, but we can assign a const into it, right? So basically, const doesn't do much for Rvalues. We will see some exceptions to that later. Indeed, there are also storage classes. So who here thinks this is saying immutable int? A few suckers, okay. So well, actually, yeah, that's usually what people think it means. What it actually is saying is this is an immutable int x equals 2. And then this is also a bit confusing because you can actually write the type immutable int. That's just not how this is parsed, right? So if you have this kind of storage class, it applies to the entire declaration, not to the return type. So how in practice those things interact is that you can only specify one of them, and then the other one will be automatically added. You can actually write this. It's not considered redundant. And this is especially important for functions. So for example, here we have an immutable int pointer foo, and to like many people, this looks like immutable int pointer. But actually, it's the same as for the variable, and it applies to entire declaration, which is the same as qualifying the implicit context. So if this is a member function, it qualifies to this. If it's a local function, it says you can only access immutable closed-over variables. So this can sometimes throw off people because ref also qualifies a function, but in fact does relate to the return value. Right, so even for ref, this is the same as this. So this is a ref function, but actually what it means is it returns by ref. So and then there is this one detail about ref and delegate types. So who thinks this function returns by ref? Nobody. Okay, this function actually returns by ref. That's clearly what it says, right? Who thinks this function returns by ref? Nice. Yes, you're courageous and right. Now, who thinks this delegate returns by ref? Well, it already says it doesn't, right? So you should get the hint. So what this is actually doing is it is saying the delegate itself is a reference. Then this should say that the delegate returns by reference, but the parser rejects it. And that's, even though for immutable, both of those things work, right? So maybe that's something we can fix on the hackathon. For functions, there is this interesting detail that you can overload them. So the type of an expression actually drives behavior, which means you cannot directly erase types from D programs. You first have to do some lowering of syntactic sugar. Here, the constant R value actually strikes back. So here's an actual use case for this. So if you call a foo of 2, it will call the first overload. If you, however, call foo with a constant, it will call the second overload. I mean, I don't know why you would do this, but it works. Then another thing that's quite interesting about overload resolution is that actually if you have overloaded functions overloaded on delegate types and you put in this sort of template delegate literal, it will actually result in a template instantiation per overload while it's trying to match. And you can actually, in this delegate itself, introspect on the argument type in order to decide what is the return type. And so if you ever wanted to implement this sort of automatic enum scope lookup, this is one way to do it. Okay, so next point, there is a type deduction in D. So here we have auto x equals 2. So who thinks auto means infer type? All right, a few suckers again. So auto actually doesn't mean infer type. It's not a wildcard replaced by a type. It's just needed here to introduce a declaration, and what it's actually saying is, automatically determine where to put this variable. This is the same meaning as it has in C. Because, well, if you didn't write auto, it would just try to assign to an existing C. You can actually also have type deduction if you just put any other storage class in front of the declaration not to introduce it. So this is another way a const R value may actually take effect. So here, this x will actually be a const variable, even though it doesn't necessarily mean much on the right-hand side. So some limitations of type deduction in D. So one is that it only works in the forward direction. So for example, here we say auto x equals empty array, and then we try to append, maybe it looks like, it's readable, okay. So we try to append 1 to the array, and it doesn't work because D thinks x is a void array. And then if you actually say, well, no, it's an int array, then it works out. Yes?
Isn't it an array of no-throw?
Very good point. No, it isn't, but it should be.
I believe it's an array of no-throw bottom types.
Well, it should be an array of no return, but it is currently still a void array.
Okay, thanks.
Yes. Yeah, but I fully agree. It's also on the slides. So another limitation of type deduction is that you can actually break code by returning a more refined type. So here we have D that refines C. And we want to return, so first we have two functions that return C. And now we want to change foo so that it returns D. And this actually breaks the caller because of type deduction. And if you write the type explicitly, everything works out because a D is still a C, and we can reassign result. So basically, be careful when using type deduction with code you don't control, and may change result types. All right. So I mean, you've already seen maybe I wasn't too happy about some things. That is because you cannot be happy about everything. So there's a huge list of things that you want the type system to satisfy, and not all of them can be true at the same time. And the art of designing a type system is basically finding synergies between those things. And and kind of you have to choose. So for example, expressive type systems are nice because your code is self-documenting, that the compiler may even check it to some extent. Metadata is accessible by tooling with standard meanings, and it detects errors more efficiently than tests would. So, I mean, probably a lot of you have had the experience where you wrote a script in Python, you ran it for like 5 minutes, and then in the end it crashed while printing the result because you got some formatting things wrong. That's something that the types help you with. They won't even let you run the code, right? But you probably still need tests unless your type system is maximally expressive. Expressive type systems can lead to some annotation overhead, and those type systems are more likely to become non-modular if you make them more expressive without keeping this in mind. One point is that most languages tend to evolve from less expressive type systems to more expressive ones. And this is actually much harder than just designing a simple type system that is expressive from the start. But there are very simple systems that are very expressive. This is also something that people sometimes don't understand, because their experience is as languages get more expressive, they get more complex. But it doesn't need to be that way. It's just hard to do in practice. So I talked about modularity. What is this? Modularity means you're able to factor out patterns into functions or aggregates. And type information, therefore, must be able to cross function aggregate boundaries. So now we will have some example of a successful refactoring. So here we have y that is x plus 3. So what you can now, of course, do is just say, well, we have a function that adds 2 numbers. And then we can replace x plus 3 by a function call. And what this function tells you is what it expects and what it returns. And in this example, this is all the information you need. This is, however, often not the case. So for example, here I'm taking advantage of value range propagation to put the lowest 8 bits of x into a u-byte y. Now I try to somehow extract this into a common pattern where we mask out a certain number of bits. And now it doesn't work anymore because mask low returns int. And unfortunately, there's actually no way for me to fix this, because the type system here is tracking information, namely value ranges, that is actually impossible to thread through this function. So in order to make this refactoring type check, we would need to annotate somehow what is the range of the result based on the range of the arguments. So this brings us to the next topic. So there's type safety, and if you have a type-safe language, your types define invariance on the program state. In D, we have safe values for each type, and some types also come with constraints how they can alias. And all operations, like safe operations, have defined behavior if the invariants hold, and they preserve invariance. Of course, type safety is not always, it doesn't always hold. So for example, here we have a Boolean that is initialized to void, which means it's not initialized. And then we have if B, it writes B is true. If not B, it writes B is false. So who thinks this prints B is true? Who thinks it prints B is false? Well, I mean, if you've raised your hand at any point in time, you're right on my machine. Basically, it will print both B is true and B is false. And this is the kind of behavior you can get if your program is not type safe. Of course, type safety comes with its own trade-offs. So, like a really nice thing about type safety is that programs never lie, and types are actually compiler check documentation. There is quite a bit higher confidence in refactoring because, well, at least you will not introduce undefined behavior. So your tests will actually be able to catch bugs. A nice thing about type safety is that it can support the safety guarantees. An issue with type safety is that, of course, perfectly fine programs may still be rejected. And because people like type safety and they don't like having their programs rejected, you always get this sort of pressure to increase expressiveness and modularity of your language. So as a consequence, you usually get a bit larger annotation overhead. So this is what is colloquially known as attribute soup indeed. So because D, of course, doesn't do either no type safety or type safety, because it's D, it does both, right? We have system. This is an annotation for functions, and basically this means types are suggestions, and programmers are infallible. If your function has a bug, and somebody decided to call it, it's on them. They shouldn't have trusted your function, right? Then there is trusted, and this means the function has a type-safe interface. So it behaves exactly like a function that is safe, but internally, maybe the compiler doesn't know about this. One interesting thing here is that the programmer of the function is considered infallible by the language, and the caller is a bit restricted, but adversarial. So the caller may not pass unsafe values to your function, which means it's restricted, but the caller is not infallible. They're actually actively trying to break your function. This also means that people who write trusted functions are the only people who are actually able to be blamed for memory corruption. So if you do memory corruption in system code, well, you're not the one who called your function, right? It's not on you. If you wrote memory corruption in safe code, well, it's not on you. Somebody who wrote the trusted function screwed up, or just the language didn't type check your program properly. And I actually didn't say what safe means, right? This means programs have defined behavior. Programmers are adversarial, so not competent at all. It doesn't really matter. I mean, you can write safe code even after getting high on milk at DConf. And callers are restricted but adversarial, which also means that safe and trusted have kind of the same interface. So from the outside, it doesn't matter whether a function is safe or trusted. So the overall goal of this entire thing is that type safety and lower-level control coexist in the same program. That trusted functions or the language should be to blame for any remaining holes in safe code. So this introduces a sort of compile time modularity for memory safety. The runtime effects of memory unsafety are still unrestricted. So if you screw up memory safety in a trusted function, where this manifests may actually be in a safe function. So more generally, D prevents auto side effects. So all function types have an effect annotation. If it's left out, that's still an effect, right? It just means it's unrestricted. You can do anything that the language allows. So as we see in safe means no memory corruption. It also means no undefined behavior, because memory corruption and undefined behavior are kind of related. So this is the data side, and this is the behavior side. Then pure is intended to mean no mutation of global state. It's mostly that. It's actually by design mostly that. One design decision I agree with is that pure functions can allocate memory. One design decision I don't really agree with is that pure functions are allowed to mutate float rounding settings. There is no throw. It prevents throwing of exceptions, and there is no GC. It prevents GC allocation, and indeed it also means it prevents GC pauses, which is something people sometimes don't appreciate, because indeed a GC will only collect if you try to get more memory out of it. So, of course, there's a vast number of other effects one could prevent, and of course we probably will prevent at some point, because you need to make that attribute soup a bit more tasty. I have a few ideas here, but probably that's not what we're going to do. I intentionally didn't add anything here that's supposed to be realistic. So this effect tracking still has some practical challenges. So one issue is that pure is underspecified. So I think it is currently not clear when a function can be trusted pure and when it cannot be trusted pure. Because I don't really know what is the invariant that is enforced by the pure qualifier. I mean, it prevents some things, like it prevents you from accessing a mutable global state, but it's not so clear what exactly is the invariant that this enables. Often, another issue is that people want to check their code non-transitively, so they don't really care about effects that happen somewhere else, but they really want to make sure that they're not the ones introducing them. And currently, there is not really a good story for that. In particular for trusted. Trusted is quite tricky to use correctly. So it is hard to specify in a fine-grained way which operations one wants to trust. And this is particularly an issue in generic code. So this means that even the standard library now uses trusted lambdas with an unsafe interface, like this kind of thing. This has much better ergonomics than what would be the intended use of trusted, but this is also a completely wrong way to use trusted because this lambda does not have a safe interface. So it interacts with state that is controlled by safe code outside. And if you remember, safe code can be changed by people who are drunk or high or whatever. You are not allowed to trust safe code from within a trusted function. So probably the language has to make some concessions here because the current state is not all that nice. So another point is about inference and defaults for effect annotations. So auto functions infer their effects. Functions in template instances also infer effects. But currently there is no other way to turn on inference if you specify the return type of your function. So maybe that's something we can address. Another thing that we maybe could improve is that inference currently is sometimes a bit unreliable when there is a mutual recursion between functions. Oh, Walter has a comment.
There is a way to turn on the inference if the return type is specified. You just add opening and close parens to the parameter list and make it a template.
I fully agree, but there is no other way, right? There's like the first way, there's the second way. You describe the second way, but there's no other way. I mean, this way that you specified that works. One issue is that your function will not be type checked unless you instantiate it, and the error message will happen in the wrong place. I mean, it's a small ergonomic detail, right? But maybe we could allow auto on functions that also specify return type and then infer attributes or something like that. So there was tip 1028, and it proposed making safe the default. So ultimately it was retracted because safe is not saying default for external C function prototypes. So personally, I think you should not be able to annotate external C function prototypes safe at all. But that's kind of not what the language does at the moment. And one point that we certainly could address anyway is that it would be nice if there was a way to switch defaults without disabling inference. So another way detracks effects is mutability of Lvalues. So you have an unqualified type. It can be mutated. It may not be shared. So, I mean, instances of T, like variables of T, can be mutated, right? Then a mutable T cannot be mutated at all. It can be shared freely as a result. I mean, I don't know if this is the best design, but it kind of seems to make sense as well. Then const means you cannot mutate something for the current reference. The other people may mutate this, and you may observe the mutation. And for about inout, we will hear a bit more later. Shared means you can share, but you must properly synchronize accesses. All those qualifiers are transitive, and no mutation really means no mutation. And I cannot stress this enough. So I've a nice quote from my office mate is, const is so strong and provides such strong guarantees in D that it's essentially almost useless. So personally, I don't use it very often, and you should also be careful because it will really restrict you. All right. So let's get back to the attributes. So the challenge I've set up is to create a delegate that composes two int delegates. So here, the type of that thing will be a delegate. It is to int delegate that takes an int, right? And it will return an int delegate that takes an int. The function itself can, of course, be safe, pure, no throw, and no GC. And this is my implementation. Who can see what's wrong with this? I mean, yes?
The delegate are not safe, pure, no throw, no GC, so when you call it's going to fail.
Well, I mean, it doesn't call it, right? It just returns an int delegate that returns an int.
All right, you're in front of the, not for me, so.
I'm standing in front of it. Nice. Well, I mean, I guess we should get going. So the issue is basically that those delegates are unqualified. So if you pass in two safe delegates, the result will not be a safe delegate. And basically, currently, there is no way to write a polymorphic compose function in this way that actually correctly preserves the qualifiers. And this is a pure modularity problem. So if you actually inline compose into its callers, this will work because here this literal will automatically infer the right qualifiers. So a less contrived example that often comes up in practice is the virtual op apply. So we have some AST nodes, we have some components, we iterate over it with op apply. In practice, people now have to kind of write op apply for all combinations of qualifiers on op apply and the delegate. And this is kind of a burden on library offers. And in practice, most library offers only decide to support some subset of qualifiers. So maybe they will require the callers to pass in a safe delegate, or the op apply will not be safe, and so safe callers cannot call it, and so on. So in general, D is usually designed in a way that allows type checking the identity function. So, and in practice, you can get relatively far templated functions. So for example, this ID function here works, right? It will preserve qualifiers correctly on the delegate. And the issue with templates is, by one, it's either templates or virtual calls, so you have to decide. And in practice, you usually decide for templates, and then you hamstring yourself because you won't have virtual calls in your program. And one reason for this is that if D does not match lambdas very reliably, and that's maybe also something you could address. In total, this leads to template load and somewhat larger compile times if you want to support all of the attribute combinations. This entire thing has, of course, happened before. So it's also the case for mutability qualifiers, and this is why inout was invented. So basically, this single function replaces all of those three, and it has a single address. And you could, in principle, think about doing exactly the same as for the effect annotations, but I will argue against it because I think inout has some issues. So one thing is there's only one inout qualifier. But there can be multiple functions in your program. Which function relates to which inout annotation in any given context is determined by ad hoc rules, and I think they're somewhat inconsistent. So for example, here we have an ID function that returns a delegate that turns an inout int into an inout int pointer. We actually cannot call this with a function that takes an immutable int and returns an immutable int pointer. This is because those inouts here refer to the function call that occurs when you call the delegate, and not to the function call that occurs when you call the identity function. And there's actually no way to write this identity function here that works for immutable, const, and mutable. Another issue with inout qualifier is that inout qualified data can be stored in aggregate. You cannot have a struct field of type inout in pointer, for example. So this also means that inout is incompatible with most of the Phobos range API because it permits zero data abstraction. I mean, Phobos anyway goes out of its way to accommodate inout, and I think it's maybe not worth it. So of course, if you don't like it, you try to break it. So one observation I made is that nested functions actually share inout with their enclosing function. So if there's any inout in the closing function. However, as you've seen, high-order functions within return types have their own inout. This is inconsistent, and interestingly, the obvious way to exploit it has been patched. So here we have a bar. It looks like an inout function, but this inout here is actually the same as this inout here and this inout here. So because it returns inout in pointer, we can actually return the parameter of the enclosing function, and then we can return bar. And this is accepted. And then an interesting thing that happens is if you look at the type of foo, you actually get something that turns an inout int pointer into an inout int pointer delegate. But if you call this function, what you get is not an inout int pointer delegate as claimed. What you get is a const int pointer delegate const int pointer. So what the compiler is doing here is it's fixing an inconsistency here with an inconsistency down here. And in this kind of tricky way, it prevents me from breaking the type system. So a nice consequence of this is that actually the generic template identity function preserves the type for all argument types. Well, actually it doesn't, right? So ironically, there is this type T here, inout qualified inout int pointer delegate, that if you pass it to an identity function, will return something of a different type than what you passed in, because some of the inouts here will be replaced by const. So the effort to preserve type qualifiers through an identity function actually prevent us from preserving types for an identity function. And then, of course, there's a way to circumvent the patchwork. So here I can mutate this immutable global, or actually a DSEC fault at runtime in this case. I'm doing the same thing as before, but now I'm actually just closing over the address of bar. And then if I call it here, it will not do the const patch, and we will actually get an inout function, and then those two inouts get conflated. We pass a mutable thing, which means inout is instantiated with mutable, even though this thing here is originating from this inout, which is instantiated with immutable. So we get a type panning between arbitrary qualifiers. The return parameter attribute has some similarities to inout, but it's not as broken. So it is still the case that interaction with nested and higher order functions seems a bit tricky, but there's a way to make it work. Return scope pointers and return references cannot be individually stored as struct fields, but at least you can store lifetime limited things in structs, right? So there's only one name for return attribute, that's the same as for inout, which means lifetimes tend to get conflated. However, because you don't need substitution, return avoids many of the inout pitfalls. So there's another comment.
Okay, if you have multiple returns in the parameter list, the compiler will select the one with the smallest lifetime as the lifetime that's actually being returned.
Yes, exactly. Which means you cannot preserve the longer lifetime of one parameter if there is some parameter with a lower lifetime. Yeah. So one way to address this that is often done, and it's also done by languages like Rust, is to have some sort of parametric polymorphism. So for example, here we explicitly pass in the mutability, and this allows you to have different mutability for the argument and the return. So you can actually thread through a polymorphic function through a function, and it works out, or you can have a polymorphic function that threads through a function. There's the same thing you can do for effects, and then you also get to solve this op apply issue in a quite nice way. Of course, one issue I've heard mentioned in this context is that this may increase compile times quite significantly, and then maybe it's also not worth it. So we'll have to see how to address this kind of thing. An interesting thing about CTFE is that it's technically part of the type system, but CTFE functions cannot manipulate types directly, and they should probably also be fixed. Then a nice tidbit is that forward references and introspection. So here, if x is not defined, we define x. Some people think they should work, some people think it should not work. Here we thread it through y. I think it should not work. Maybe some people think it should work. At the latest, at this example, people start agreeing with me that it should not work because which variable here is defined actually depends on which module you pass first. You get inconsistencies between different compilation units. And I actually wrote an experimental frontend with explicit dependency tracking to try to address this. So it catches ambiguities and contradictions. Unfortunately, it stopped compiling with DMD 61. Ironically, the reason was I went too crazy with code generation introspection. So the problem I tried to fix with this caught me. Of course, no talk about types and tuples would be complete without the infamous type tuple. So I won't go into details here, but it has some restrictions, and I think it is not a tuple type because it's not a type, right? It's a nice metaprogramming tool, but it doesn't fix the need for tuples. So what is a tuple? That's something that contains multiple values. You can get back out whatever you're stuck in, and it's not more than the sum of its parts. So it's a product type, but it's sum. Yeah, it's a bit annoying. It sounds a bit like struct, and there is a standard type const tuple, and the question is what is missing. So this is a simplified implementation of that. The actual one is a few hundred lines, I think. So what do you use a tuple for? You create ad hoc groupings, and for very localized data structures or for returning multiple values. So you shouldn't really use it in interfaces all that much. So what is missing is actually you cannot stick things into tuples. So you cannot stick an inout pointer into tuple. You also cannot get things out because of return. So we cannot get back out A and return it because it has been its lifetime has been conflated with the local variable B. So at the moment, it's kind of not achievable to have tuples so you can stick things in and get them back out. But we can opt for the next best thing, which is destructuring. And actually, there was a pull request in like 2011 that implemented destructuring. It was never pulled, and basically the issue was, well, we need the full tuple design. Otherwise, this may restrict us too much. So the only thing I think that's wrong with this proposal is that this looks weird. Otherwise, I would say slightly generalize this and ship it now. Then there's this one thing that actually slipped past Walter and Andre. You can actually, so here, this is not yet it, but so you have x and y, we iterate over an array, so we get index in the tuple. By the way, this formatting really should be fixed, it's completely useless. But if you map the array such that it becomes a range, it will actually match the tuples. This is a bit annoying, and it actually runs exactly into this thing where you have to have a design that now accommodates this. So why are there no tuples? So I implemented static for each. The issue is that there is a very small design space for static for each. In tuples, there are many moving parts and has to fit into the existing language. Different syntactic preferences exist. I think the others also have some issues, not just mine. And then, of course, you want all of those different things. And I tried to write this up in a dip. It still needs some updates, and any help is, of course, welcome. And finally, here are some hackathon projects that I think would make sense. Yeah, so sorry for not managing my time right. I removed a lot of things from this talk. And I know all of you wanted to hear about tuples, and now it didn't work out. But feel free to talk to me directly offline, or now during the question session.
Oh, thank you, Timon. That was actually your first DConf talk. I didn't know that. So another round of applause for a first timer, hey? All right, questions time. Again, I am checking Discord and YouTube here, but let's start with John over there.
So you've shown a lot of complexity in this, right? You're showing all the ways that all the complexity we've got doesn't quite add together, and even when it does add together, it's pretty complicated. Do you honestly think that it helps write more correct, useful programs faster with less errors?
Well, I mean, there's always the distinction between user code and library code. And usually what happens there is the library author writes something, a user complains. And what you want to happen in those circumstances is the language has an answer for it that the library author can just take off the shelf. Right now, I think library authors have a lot of frustration because users come, they have valid concerns, they want to support them, but it's basically impossible.
More questions? Anybody with a question? We'll read out this comment from Ricky, though. It is unfortunate that there is no way to disable TLS transitively. This is coming up quite a bit lately. It would be cool to see D have a solid effect system.
Want to thank Timon for this talk pointing out every mistake I've made. But I like that. And a lot of your examples I want to put into the D specification, so at least by understanding those things, they'll get to understand the type system a lot better, and it'll be less confusing for them, even if they find the holes to be frustrating. So I really appreciate the work you did putting this together and enumerating these issues. I think it's really great work.
Thank you, and I also really appreciate all the work you did on the parts of the language that I like. Which is actually a lot. I mean, in practice, I mean, people run into some of those issues, but some of them don't matter all that much.
Somebody else has got to have a question. Yeah, over there.
In terms of the use of tuple, like in the Python world, a common use is just to return multiple values from a function, let's say like a function and its gradient, and having a nice clean syntax to do that makes writing code very quick. How realistic do you think it is, based on the work you've done on your dip, have something like that in D?
Well, I mean, I have an implementation that kind of works. The devil is in the details. Basically, one issue that needs to be addressed is what syntax do we use? And there's, of course, a lot of bike chatting on this. And the other one is how exactly does it work out with lifetimes? Because in D you have like moving, you have destructors. So how that interacts with matching is an interesting question. But I mean, it's definitely realistic that this works. I mean, we can make it work. I have a branch here that. So here you can actually return a tuple and match it, and it will have the right semantics, except maybe if you have destructors involved.
Yeah, we got one more question.
In my experience, the only thing that inout buys us is that if you have like member functions that treat like, mutable, immutable const with equanimity, then you can use it. But otherwise, I haven't really seen any use cases. So I'm just wondering, what does all this added complexity to support inout actually buys us?
Well, I mean, I think there are nice use cases for inout, right? Probably currently it's not worth it, because I think there are simpler designs that achieve what inout wants to achieve and do it like better. The nice thing about inout is, I guess, it's really easy to type check. So you don't need to have some sort of scoped context, and so it compiles faster, which I think is, I think that's better.
But for users and library creators, I don't know, do they really care about that?
I mean, personally, I don't really care about it because I tend to avoid qualifiers. But I mean, some people like it.
All right, cool. That's it for question times. Thanks again. All right, you all know the deal. We got 5 minutes of break.